Hey everyone, and welcome to this explainer. I am absolutely thrilled to be diving into this with you today because we're going to be looking at one of the most fascinating intersections in modern science. As someone who kind of lives and breathes that multidisciplinary student life, always trying to connect the dots between advanced physics, complex math, and computer science, this topic is just an absolute dream. Today, we're literally tearing down the absolute limits of traditional computing to figure out what comes next. We are going beyond the binary barrier to unpack the quantum hardware revolution. Let's get into it. To instantly grasp the massive, real-world stakes of what we're talking about here, just listen to this for a second. Everything we know about modern security is about to become obsolete. Traditional silicon gates simply cannot keep up. Welcome to the era of exponential power. Guys, that isn't science fiction. This is the impending reality, the very foundation of our digital privacy, our scientific research, and our problem-solving capabilities is on the verge of this massive, exponential leap.
All right, Section 1, from gears to transistors.
Okay, before we can truly appreciate where we're going, we absolutely have to map out how we got here. I love thinking about technology as this ladder of abstraction, right? Back in the 1800s, early computing attempts literally used decimal numbers represented by metal teeth on mechanical gears. It was clunky, physical, tangible machinery. Then, fast forward to the 1900s, and we moved a step up that ladder to electronic transistors, where we started manipulating electricity. And now, in the 2020s, we are making the completely mind-bending jump to manipulating actual atomic quantum states. To really understand our current electronic era, we have to talk about Boolean logic. Traditional transistors act a whole lot like a water spigot. It's actually a beautifully simple analogy. If you open the tap, electricity flows, and that registers as true, or a 1. If you close the tap, the electricity stops. That's false, or a 0. This incredibly simple, rigid on and off switch is basically the entire foundation of all binary Boolean logic. But here's the truly wild part. The sheer scale we've achieved with those microscopic spigots. 10 billion. Inside a single modern CPU die, engineers have somehow managed to pack up to 10 billion of these tiny transistors. They form this multi-layer labyrinth of nanometer-wide highways, successfully processing true and false statements literally billions of times a second. It is, without a doubt, an engineering marvel. But we've got a problem, a big one. We are fast approaching what's known as the 2026 silicon wall. We're hitting hard physical limits, where these transistors simply cannot get any smaller without quantum interference completely messing up the signals. Fabs just can't shrink them forever. So, to keep advancing, we need a quantum leap. We have to transcend those binary constraints and kick off a radical hardware revolution. Which brings us to Section 2, enter the qubit. So, if we're leaving binary behind, we've got to shift our focus to our new superhero solution. What exactly is a qubit? Well, a quantum bit is the basic building block of quantum information. But unlike standard bits, it's capable of existing in multiple states simultaneously. It is this incredibly elegant and honestly entirely necessary leap beyond the rigid limitations of those traditional logic gates we just talked about. Let's compare these two paradigms side by side. Binary logic is like a fixed light switch. It is definitively either up or down, 0 or 1, right? But quantum logic operates on fluid probability. Imagine a continuously spinning sphere. In math, we often call this a Bloch sphere. The qubit can exist anywhere on the surface of that sphere, which allows for these massively complex probabilities instead of just absolute rigid certainties. And this whole spinning sphere concept, that's driven by a mechanic called superposition. Superposition is a phenomenon where a quantum particle exists in multiple distinct states at the exact same time. Well, until it's measured anyway. Think of a single photon of light being both horizontally and vertically polarized at the exact same moment. This mechanic right here is what eventually enables massive exponential parallel processing. All right, Section 3, fragile atoms, stable silicon. I really want to heighten the engineering drama for a second because the contrast between these two systems is just staggering. A standard silicon CPU is a robust workhorse. It pushes 1.3 volts, needs liquid cooling pumps, and gets hot enough to double as a space heater in winter. It totally thrives in chaos. But a quantum chip? The exact opposite. It is incredibly fragile. It requires near absolute zero freezing temperatures and these highly isolated vacuum chambers just for the delicate quantum logic to survive without collapsing. And the precision required to make this work is mind-bending. 1 nanometer. Engineers are now using advanced scanning tunneling microscopy at super low temperatures to pinpoint the exact location of a fragile phosphorus atom, which acts as our qubit, to within a single nanometer inside a silicon lattice. They literally have to search a 5 nanometer grid just to find the one single location that perfectly matches, single atom accuracy. It's breathtaking multidisciplinary engineering.
Moving on to Section 4, the power of entanglements.
Okay, so we have these incredibly delicate qubits perfectly placed. Now what? Enter entanglement. This is a quantum state where particles become deeply linked. This means the measurement of one instantly dictates the exact state of the other. Multiple distinct qubits become inextricably reliant on one another to hold complex information.
Let's actually walk through how this magical-sounding reality works in practice, in what's often called a Bell state. Step 1, you entangle 2 distinct qubits. Step 2, you physically separate them. Step 3, if you measure the first qubit, you instantly, without even looking, know the exact state of the second completely separate qubit. Going back to our water analogy earlier, it's like checking the status of one water spigot and immediately knowing the exact state of a completely separate spigot miles away. It shouldn't be possible, but it is.
And finally, Section 5, solving the impossible. So all of this advanced physics is incredible. But what's the actual point? Let's tie these microscopic phenomena directly to some massive real-world applications. Instead of just brute-forcing math with classical tech, quantum computers will use things like Shor's algorithm to effortlessly find prime factors. Instead of hitting binary logic walls, we totally unlock exponential processing. Instead of guessing chemical formulas, we can perfectly simulate highly complex molecular structures natively. We aren't just getting faster computers here. We are getting an entirely new paradigm of problem solving.
So, to summarize our core takeaways for this post-silicon era, quantum tech is going to crack modern cryptographic security like RSA, which, by the way, is exactly why everyone is rushing to build quantum-safe encryption right now. It's going to revolutionize scientific research. By accurately simulating molecular structures for medicine and new materials, it achieves exponential processing speeds through phase and superposition, and ultimately it just completely redefines the absolute limits of hardware logic itself. So, I want to leave you with this provocative thought to chew on. When binary logic finally becomes a relic of the past, when those tiny silicon spigots are totally replaced by the infinite possibilities of the spinning quantum sphere, what impossible puzzles will you solve with that kind of exponential power? This multidisciplinary leap we're taking is truly just the beginning. I really hope this explainer sparks some curiosity in you to keep exploring the quantum frontier. Thank you so much for joining me, and keep questioning the limits.